Now let us look at decimal to a different number system conversion. Let's take hex for example. So problem here is we have to convert 15,434 in decimal to corresponding hex representation. Hex, a short form of hexadecimal number system. So as we know, hexadecimal number system has base 16. It has 16 symbols. So we keep dividing it, this value with 16 and compute its quotients and remainders. So this is a little bit tedious than dividing by 2, of course, but we can use calculator or something. We can come to this quotient and remainders. So question is why it is a, right? So if you divide this 15,434 with 16, your quotient become 964 and remainder become 10. Okay, and 10 is represented in hexadecimal with the symbol a. It doesn't matter whether we write a capital A or small a, is the same thing. Okay, just whatever whatever is convenient for you to write down, we can, but stick to one convention. If you represent everything with a lowercase a, b, c, d, f, you stick to that. You don't mix up. That doesn't make sense. Like writing a in small case and b in uppercase in a hexadecimal representation. But if you choose to write it with all capital, it's also okay too, like capital A, capital P, till capital F. Anyway, so we determine the remainders and also convert it to corresponding hexadecimal symbol. So here in this case, the remainder was 10, so that corresponds to your symbol A. And then the next step, quotient 60 and remainder is 4, and next step quotient 3 and remainder was 12. So 12 is represented in hexadecimal as C. All right, and then the last step, quotient becomes 0 and remainder 3, and we all know this is the most significant position, least significant position. We loosely call it a most significant bit, MSB or LSB. Its bit is about the binary system. So the point here is that this is the most significant symbol position and this is the least significant symbol position. We need to write from down to up in this process. So our converted hex form is 3C4A. 3C4A, and of course we need to write down its base. Though it is kind of apparent that, okay, we're possibly talking for 16-bit hexadecimal, 16 symbol hexadecimal representation here. A does not belong to decimal or binary or octal. But remember, as I said, like we can define our own system. Let's say if we decide to construct a number system with 20 symbols in it instead of 16, that system will include, of course, A, B, C, D, may include A, B, C, D, E, F, G, H, I, J, right? And so in that case, we don't know if it is that new system or hexadecimal. So it is always needed to write down the base when you are representing a number, especially when you are doing dealing with different number systems in a problem. All right, so here is a way, and then here's a table that you need to remember, and that will help you in at least convert 4-bit, 8-bit till 8-bit numbers very quickly. And we'll see we can use the same table, a little bit extended form, is in quickly converting binary to hexadecimal. Okay, so here is a map, the hex digit and what's the corresponding decimal value. So A is 10, B is 11, till F is 15. So once we remember these, then let's do this hex to decimal conversion. Let's say I have this hexadecimal number D5C2 3 base 16 and I need to convert it into a decimal value, we start with the similar thing as we did for the binary, which is the hexadecimal position, the indexes. It is the, I think 1, 2, 3, 4, 5. So index starts from 0, 1, 2, 3, 4. And then we compute decimal weight of each index position. So first would be your decimal weight would be base of the number system, which is now base 16. This is 16 to the power 0, which is 1, and then 16 to the power 1 is 16, then squared, then cube, and then to the power 4, just like this, right? And then we place these symbols D5, C2, 3 under those positions, and then we do this thing simply, like D, the decimal value is 13. So we multiply by 13 decimal with the decimal weight for at this point, which is 65536, with a huge number. And then corresponding 5 multiplied by corresponding decimal weight, and then 12, which is C's value, corresponding decimal value is 12. So 12 multiplied by 256, then 2 multiplied by 16, and 3 multiplied by 1. Now if we compute this entire thing, our decimal value become 875,555. Now one thing to note, see, this is a huge value and we need to use 1, 2, 3, 4, 5, 6 decimal symbol where we can represent the same value with the 5 hexadecimal symbol. Now think of, like, if you want to convert it into the binary, how many bits you would need. All right, how many bits you would need? I would say 20. Okay, I would say 20 without even thinking much. That it needs a 20 bit, these big values, and this seems like a magic. Okay, that how come I so quickly can tell you that it needs 20 bit to represent the value, this value in binary number system, or this value in binary number system. I'll tell you, like, in couple of minutes. All right, so now we see that this also corresponds. We use this formula that we discussed at the very early of this lecture session. This is sigma of your I to n minus 1 and decimal value at the position I multiplied by the base to the power I. That is the formula we'll be using, and we are practically using that in a little bit different way. Okay. Now this question, hex to binary conversion. One way, of course, you do this decimal. We all know how to do it. Then to the binary. Reverse is also true. Binary to decimal to hex. Now it needs couple of steps, right, involved there. Now there are some tricks through which we can directly change from format wise, change from hexadecimal to the binary. All right. To do that, remember that earlier table that we talked about the hex digit and the decimal value. We extend that table now with a 4-bit corresponding binary values. Okay, so 0 is 0000, 1 is 0001, 2 is 0010, and so on and so forth. So we do compute it for every hex digit. Okay, and it is very useful to remember this table. Very useful. Okay, so that on fly you can do conversion very quickly from a hex to binary and back. All right, so how do we do it? Let's take this same example or on an example. So this is 5C23, right? And then how do we convert it to binary? So what we do, take each of these hex digit and bump and write its corresponding binary 4-bit binary pattern. All right, so here is C, corresponding binary pattern is 1100, 5 is 0100. So we'll be using this table to convert this this sequence of hexadecimal symbols into corresponding binary symbols, and each of this symbol will be converted into 4-bit. All right, so 5 will represent as 0 1 0 1, C will be 1 1 0 0, 2 will be 0 0 1 0, 3 will be 0 0 1 1, and that becomes your binary representation of the value represented by this hexadecimal pattern. All right, so blow up each hex digit into 4-digit bit pattern. Now you see like how in the previous two slides back or one slide back, how did I tell that, hey, this 5 symbol hexadecimal value will be represented with 20-bit, because I knew this process. Each of the symbol will be expanded into 4 bits, right? So if my original hexadecimal has like 5 symbols, I'll need 20 bits, 5 into 4. Each symbol will be expanded into 4 bits. So 5 symbol, 20 bit, straight answer, right? Here, 4 symbols, 16 bit, right? So you might ask like why we choose like 4-bit, why not 5-bit, why not 3-bit? Okay, so let's look at the table very closely. First of all, with the 3-bit, the range, if you remember the formula of the range, it is 0 to 2 to the power n minus 1. So for 3-bit, your range is you can represent 0 to 7, right, which is not sufficient. Now for like if it is for 5-bit, then we could represent like 0 to 31, right? 16, 32, 2 to the power 3 is 8, 2 to the power 4 is 16, and 2 to the power 5 is 32, so 32 minus 1, okay, 0 to 31 with the 5-bit. Okay, we don't need it, like how much we need? We need 0 to 15. Okay, now if you look at the 4-bit, range of 4-bit will be 0 to 2 to the power 4 minus 1, which is like 2 to the power 4 is 16 minus 1 is 15. So I can represent with a 4-bit range of value from 0 to 15, which I exactly need to cover all the hex digit or hex symbols, right? We have 16 symbol, we need 4-bit. All right, so in general in this context, let me tell you that if you need to represent n number of things, okay, it can be a different symbols or different objects and things like that. In general, if it is n number of things you need to represent in a binary form, like with the unique binary values represented through the binary number system, you need minimum of log base 2 of that number. Okay, log base 2 of that number, and you take a ceiling value of that. Okay, so it is a log base 2 of ceiling value of that n, whatever n is given. Like for example, let's say you need to represent like 12 things, okay, 12 things with a binary number or binary value system. Then the number of bits, the minimum number of bits to represent that would be log base 2 of 12, and you take the ceiling value of it. So log base 12 is somewhat around, I would say like 3 point something. Okay, 3 point something, log base 2, 3 point something. It's not 4, but if you take a ceiling of that, it becomes a 4. Okay, you take a ceiling of that, it becomes a 4. So it is basically you need a 4-bit to represent 12 things. Okay, like for example, if you need to represent 8 things, so log base 2 8 is 3, so you need 3-bit for that. If you need to represent like 6 things, then also it will be like ceiling of log 6, which is like about 2 point something, and then you take a ceiling, it becomes 3. Okay, so this is very important concept, like number of bits you need to represent. You need to represent n number of things. The formula is ceiling of log base 2 of that n. All right, so we know how to do this from hexadecimal directly into the binary. How about the other way, binary to hexadecimal? So we have certain pattern, we want to convert it to the hex value. Okay, so what we do, we take that pattern of bit and then group them by 4 from the LSB side or your right hand side. LSB or right hand side. This is LSB, this is MSB. So we group them by 4. So this is one group. So we take another 1, 2, 3, 4, another group, and then we have 2 bits left. So what we do, we prepend 2 more 0 to make it a group of 4 bit. So once we have a group of 4 bit, then each group we determine its corresponding symbol from the previous table. Remember that table? So I know 1 0 1 0 is practically I know this is a value 10, so its symbol is A. This is of value 12, it will be C, and this is of value 2, that will be symbol 2. So your answer for this is straight 2CA base 16. So this is how you convert it without like converting to the decimal and then with the hexadecimal. That is like time consuming process. So if your problem given is from binary to hex or hex to binary, you can avoid that time consuming steps and do it this way.